Okay. So welcome, everybody. Thanks for being here, for attending this new seminar of the series of seminars by TalentQ Quantum Spain. So we are very pleased to have today as our guest speaker, Antonio Rubio Abadal. Antonio has accepted to give a seminar, and I'm going to introduce him. He was born in Palma de Mallorca, and he he obtained his degree in physics by the University of Barcelona in 2013. Then he moved to the ETH in Switzerland to do his master studies in the group of Andreas Wohlraff in circuit QED. And then he went to Munich to perform his PhD studies from 2015 to 2021 in the group of Immanuel Bloch. So all top scientists. No wonder that he's now a promise in our field, and he's now back in Spain. He's since 2021 researcher at the ICFO as a La Caixa Foundation Fellow in the group of Leticia Taruel. So many of you might have heard some flurry some months ago in the press concerning a new achievement in the field of quantum simulators that came from ICFO precisely. So we all hurried up and asked if somebody could report in this series of seminars about these advances. And Antonio accepted gently to come here and tell us about this thing that so the title is QUIONE, however it's pronounced. He will show us how to pronounce it. A quantum simulator based on ultracold strontium atoms. Before I let him go, I let you know that you in principle you're muted. Also, your camera is also muted. You can, if you want to make questions, you can either use the chat, and we'll pay attention to the chat if you're shy. If you are not shy and want to make questions face on, then you can just press the raise hand symbol, and then we will unlock your microphone and your camera. You're free to have your camera on or off, but then you can post your question by voice, either now or at the end of the seminar. And now, without further ado, I let Antonio thank him again for being here. So, Antonio, the floor is yours. Please tell us, explain us how to pronounce this the funny name. Yeah.
Thank you, Javier. So we usually call it QUIONE, and that will be the focus of my talk today. And I will essentially describe this machine that you can already see in this first slide, in which we built here at ICFO a quantum simulator based on ultracold strontium atoms. And so just to put ourselves in the Spanish map of quantum science, we are here very close to Barcelona, very close to also where this atomic symbol, which I think is Barcelona Supercomputing Center, is appears. And this is where in Castelldefels, a few minutes away, it's where the Institute of Photonic Science, the ICFO, is. And in particular, the group of Professor Leticia Taruel working on ultracold quantum gases. And this is how our experiment looks like, the Strontium lab. Essentially, it's an optics lab with two different optical tables. And there's a lot of electronics and optics in each one of them. And this is a relatively small setup that's controlled by a group of people, typically of 2 PhDs and 2 postdocs, so relatively small. And we try to use all these different elements that you can see. This is a close-up in our optical table. We're talking about mirrors, we're talking about lenses, we're talking about lasers, to control atoms at an individual level. So this allows us to take pictures like this one, which was collected in our CCD camera recently. So that's kind of the signal of one single strontium atom collected by the camera. And while this is already beautiful and exciting, we are not happy with just one atom, but we want to work with hundreds or even thousands of atoms and exploit their quantum properties for some quantum simulation. And with this, here's the outline of my seminar today. So I will begin by giving an introduction to the field of quantum simulation with neutral atoms. Then I will explain what are optical lattices and quantum gas microscopes, which is the key ideas for QUIONE. I will then explain what QUIONE actually stands for and what it is. And finally, show some recent results and the current status of the experiment. All right, so let me start with the first part. So we live in a very exciting time in terms of quantum technologies, quantum systems. So there's a very diverse landscape of experiments. For example, trapped ions, experiments where they managed to do hundreds of ions in Ikoki, in Innsbruck. Or of course, superconducting circuits, which resonates a lot with the quantum Spain community with this Sycamore chip that was done by Google a few years ago. Of course, also with photons, with the group of Jiangwei Pan in Shanghai has done some very impressive results. And as well with neutral atoms, as this example from the group of Jae-Yoon Choi in Korea. And all these different systems, I try to take 4 pictures that look similar, but it's very hard. Like they all look quite different. And while when we think of classical simulation or digital classical simulation, we typically think of our laptop or a supercomputing center. So there's kind of a pretty defined idea of what we usually think of. In terms of analog classical simulation, usually it looks much more diverse and broad. Like, for example, this is an AC network analyzer from MIT. So this is a 20th century electronic machine that wasn't working on bits, but was able to make some calculations on the distribution of power in alternate circuit currents. But also a lot of different devices, much older than that, also following this idea of analog classical simulation, like ancient Greece device that it's believed that was used to describe the movement of the cosmos, so the movement of the different planets. So at the end, a lot of different systems fall under this umbrella. And with digital quantum simulation, we have a similar situation. So we think often of qubits and gates and this kind of quantum simulation, but there's a much broader idea of analog quantum simulation, just having some particular experimental systems that can work to simulate some particular problem. And the main differences between these digital and analog umbrellas are that in the digital, usually one requires a qubit-based quantum computer that is digital. It will need error correction, which is one of the big difficulties in the field now. It's based on gates, and the mapping in general can be quite inefficient. So depending on the problem that we want and the architecture of our quantum computer, this might not be trivial, but it will be universal. In principle, we can map very different kinds of problems. On the other hand, an analog quantum simulator requires a special purpose quantum system. It has more tolerance for error. It's based directly on just unitary Hamiltonian evolution of the system, and the mapping will be system dependent. So it's not universal. All right. And in the field of neutral atoms, there's been quite a lot of progress in actually also the direction of digital quantum simulations. For example, experiments with Rydberg atoms in optical tweezers have been able to make impressive results that could be used for digital quantum computing. But overall, the idea of analog quantum computing has a lot of different versions or flavors. Like, for example, one can work with continuous or bulk systems and study things like superfluidity or superconductivity. One can also put atoms in cavities, so 2 mirrors that enhance the interactions with light. And this can be, for example, used to study light-matter interaction and dissipative systems. Optical lattices, which will be the topic of this talk today, which kind of resembles real material physics. And finally, atoms in optical tweezers that have also been able to simulate some spin models with high success. And I'm happy to be in the group of Professor Leticia Tarruell because we actually explore in the different labs many of these kinds of physics. So the experiment that started in 2014, the potassium lab, is actually a continuum or bulk experiment, and it's quite versatile in the sense that it's able to do very different physics. So they were able to study recently a one-dimensional topological gauge theory, but also look at exotic phases of matters like supersolids. On the other hand, we have the Strontium lab, the one known as QUIONE, which is about quantum gas microscopy, which I will explain in much detail today. And finally, the Rydberg lab that's currently under construction, and they will be able to have a much flexibility and something more similar to digital quantum computing. All right. So with this, I already jumped to the second part of my seminar, which is the introduction into the field of optical lattices and quantum gas microscopes. So first, in our experiments, we typically work with these gases of either hundreds, thousands, or even millions of atoms, and we try to prepare them as cold as we can. And that, in practice, means temperatures of the order of nanokelvin, so 10 to the -9 Kelvin above the absolute zero. And this is because we want these systems to become a quantum regime. So this quantum degenerate regime is only obtained at such low temperatures. And to do so, we need to use a series of atomic physics techniques like laser cooling or evaporative cooling that I will briefly explain today. Typically, after doing that cooling, we want to prepare our systems in what's called an optical dipole trap. Essentially, this is just a laser that's very far detuned from the resonances of the atoms, and where the atoms will kind of get trapped into the most shiny parts of it. So it's a bit like flies getting stuck into fluorescent light. So if we have a focused laser, the atoms will be essentially confined in the focus of this laser beam. And that's quite nice, but one can go beyond this continuum picture and do, for example, 2 laser beams to make an interference pattern in what's called a one-dimensional optical lattice. And then the atoms will only try to sit on these antinodes where the intensity is higher. Or if one repeats these 2 times, you can get a 2-dimensional optical lattice. And you can see this already starts to look more like a chessboard. And maybe you can see some kind of analogy with crystals, with electrons moving in real systems. And that's the key idea of ultracold atoms in optical lattices, to use these very cold quantum degenerate systems, load them into optical lattices, and use this as a quantum simulator of condensed matter physics. All right? And I will now give some examples of the power of this idea with very different systems. The most common and the first one that was realized in this way is the Bose-Hubbard model. So let's now assume we have bosonic particles that are all identical, and we have them trapped in this grid where they can tunnel, which is described by this term of the Hamiltonian. So nearest neighbors, you can have the atoms hopping from one side to the nearest neighbor. An interaction strength, a penalty that will be paid whenever 2 particles are sitting on the same lattice site, and as well as a chemical potential and an overall trap shape. And the whole idea that was suggested already in this very early on by many authors like Ignacio Cirac and Peter Zoller is that when one can observe a phase transition between 2 very different phases of matter. In particular, when interactions are relatively weak, the atoms will be completely delocalized over the whole lattice system, and this will lead to so-called superfluid or well-defined phase coherence. While if the interactions become larger and larger, eventually the atoms do not want to be sitting with each other, and they arrange in such a way that they are localized, each one of them in the individual lattice sites. And this is not only theory, but that was the first experiment that kind of launched this field, which is the quantum phase transition from a superfluid to a Mott insulator. This was an experiment that was performed in the University of Munich more than 20 years ago. And essentially, experimentally, by using ultracold atoms in optical lattices, they were able to see this transition between this superfluid phase of matter, in which the coherence is expressed by seeing some kind of interference by allowing the atoms to expand, which tends to these peaks that we see in the picture. And as the interactions are made stronger by making this lattice potential deeper and deeper, one gets a Mott insulator, in which that phase coherence, those peaks are not there anymore. And that's identified as evidence that the atoms have arranged in a non-delocalized way. There are other flavors of this Hubbard model, in particular the so-called Hubbard or Fermi-Hubbard model, in which instead of working with just one kind of particles, we work with spin-up, spin-down fermions. And the Hamiltonian looks very similar. In fact, it's a bit simpler. We mostly have the tunneling and the interaction between different particles, because note that due to Pauli blocking, identical fermions will not be able to sit on the same lattice site. And while the Hamiltonian and the idea might look a bit simpler, this system is known to have a very rich phase diagram, which is still kind of theorized. This is a phase diagram of the, or theorized phase diagram of the Fermi-Hubbard model as a function of the temperature of the system and the doping, which essentially indicates if we have like 1 atom per lattice site or rather more or less. And the motivation for this Fermi-Hubbard is that it's believed that it might describe the movement of electrons in certain materials, and in particular might hold the key into understanding why high temperature superconductors are superconducting. So while there's been a lot of work with conventional superconductors, experimentally high temperature superconductors that have been discovered, their mechanism is still poorly understood. So this could be a way of shining light into this problem, given that in general, simulating this relatively simple Hamiltonian is already very hard for classical computers. In addition, these lattices do not have to be just a square, and in fact can even be made tunable. And this is something that actually our group leader, Letizia Zarwell, did around 10 years ago, in which they showed that by playing some tricks and interfering several laser beams, you can get triangular shapes, honeycomb, and change between them at will. It has also been shown, for example, more exotic phases of matter, like this carbon lattice that was done in Berkeley some years ago, or also not even crystallographic structures, but actually quasi-crystals, so not even completely periodic potentials. And that's very exciting, that all these different kinds of materials can be realized with ultracold atoms. So the question is, what can we learn about these systems? And many of the experiments until around 10 years ago were mostly done with bulk observables. So just taking a picture of the whole cloud and imaging thousands of atoms at the same time. But quite a big revolution was the idea of quantum gas microscopy that has become in the last 15 years easily the frontier of analog quantum simulation. The main idea is that now we have our atoms in an optical lattice. We use a high resolution objective to be able to see the atom one by one. So to do that, we need to take the lattice in which the physics is happening, suddenly make it very deep to pin the position of the atoms in some particular positions, and scatter a lot of photons such that we can image them in a high quality camera. And this is challenging from an experimentalist point of view, mostly because it requires to use high power lasers. It needs very good optics to make this high NA objective. And at the same time, the atom that you have chosen needs to have an efficient laser cooling technique, right? But when all those things are kind of put together, one is able to take pictures like this one. And in fact, this is a picture that I took during my PhD in the Max Planck Institute of Quantum Optics in Munich. What we're seeing, those white dots, I have artificially put them. They represent the sites of this optical lattice potential that we generated. And each one of those red blobs is light photons, hundreds of photons that are detected from one single atom. So here we have an isolated atom, here another one, here so. You can see in the center the density is a bit higher. And in some cases, even they are so close together that it's hard to tell where one atom starts and the other one begins. But due to the knowledge of that this lattice is their potential, one can actually reconstruct their position with quite high fidelity. And this was actually done with an atomic element, which is an alkali, rubidium 87. And now you can revisit some of these experiments like the superfluid Timothy insulator, which is something that was recently done in the group of Jae-Yoon Choi in Korea, in what I think it's a very nice experiment with very nice pictures in the quantum gas microscope. The superfluid, they observed that essentially there's a bit of a random distribution of the atoms all over the space, while when they ram to the Timothy insulator, one gets a much more homogeneous fluorescence of the atoms, and one is able to conclude that there's essentially one atom per lattice site after reconstruction with high fidelity. All right, so this is quite an exciting example. If we go beyond that, we can look again at the Hubbard model. As you remember, I mentioned that this model has kind of a complex phase diagram. And in particular, let's focus on this big red blob here on the left, just for simplicity. So even at reasonably high temperatures, but below some value, one gets what's so-called an antiferromagnetic multi-insulator. And this essentially means that because we're working with spin 1/2 particles, they essentially develop a quantum magnetic state of matter in which they will try to anti-align. So whenever you have an atom spin up, the nearest neighbor will try to be spin down. And this was a goal of the field, to be able to detect this with high fidelity in atoms in optical lattices, and was done a few years ago by many groups. And this is a particularly nice example also from Munich, from a different lab, in which they were able to image, using the well-known in physics Stern-Gerlach method, the two different spin states in the lattice. So this is kind of spin up and that one spin down, and of the same cloud. And then you can reconstruct some occupation like this one, where you see the gray dots, there was no atoms. Doublons means that there were an atom spin up, spin down in the same lattice site. And then in the other positions, either spin up or spin down, these blue and red colors. And if you look a bit carefully, maybe it's not super easy to see, but you can see, for example, around here, most red atoms have a blue neighbor and the other way around. So this is kind of evidence that this state that they were able to prepare was becoming antiferromagnetically. And in fact, they were able to measure the antiferromagnetic correlations of the system and see this kind of staggered pattern of blue, red, which indicates indeed that the system has an antiferromagnetism, which is connected to this phase of matter on the Hubbard model. So that's quite exciting. And this was probably one of the most exciting results in the recent years, because as I mentioned, the Hubbard model is not easy to simulate efficiently, but it has gone quite beyond. And I will just show a result which gets a bit more technical, but of just 1 year ago, in which they were able to indeed tune the geometry of the lattice. So they started with a square lattice, similar as the examples I gave before, and they show this antiferromagnetic order, as you can see from the color of these sides. Then they were able to tune the geometry of the lattice towards a triangular one. And the thing about triangular lattices with antiferromagnetism is that they reveal what's so-called frustration, geometric frustration. So as one increases this degree of frustration, one can see that these correlations don't go so far anymore, but start to be a bit more limited. And eventually in the full triangular lattice, one finds themselves in a situation where only the nearest neighbors have the strongest antiferromagnetic signal. So this shows kinds of the tunability of the field. And in particular, it's working at regimes that could be very important to solve the mystery of high temperature superconductors. And in particular, there's some predictions that maybe not in the triangular, but in the square, but somewhere in between, there might be some important physics that could play a role into this mechanism. So that's very exciting times for the field. Another one is not to look at very cold temperatures and ground state physics, but to actually look at far from equilibrium dynamics. And this is something that I did especially during my PhD. And this was the last result that I performed while I was in the Max Planck Institute of Quantum Optics, in which essentially we used the Bose-Hubbard model in some regime, in which it can be mapped to the Heisenberg model. So maybe some of you are familiar with the Heisenberg model. It's essentially a quantum magnetism system, Hamiltonian, which describes interaction along X, Y, and Z. And when they are all the same, it's what's called the Heisenberg point. And there are quite some open questions, and it's also not always easy to simulate a system. So we were able to prepare arrays like this picture here of 50 atoms, so 1D chains of 50 atoms that were realizing this Heisenberg model. And in fact, this is how the experiment looked like. First, we initially prepared like all the atoms in one spin state on the right part and on another spin state on the left, which is why there's this difference. And after allowing the system to evolve for a certain amount of time, we saw that some of these spins had moved to the left and to the right, so a spin exchange dynamics. And in particular, this happened to be in a regime where you're expected to see what's called super diffusive dynamics. And there are some connections with some universality classes that are quite exciting. So our experiment was able to show this with a reasonably large system of 50 lattice sites and up to quite long interaction times of this Hamiltonian. And this was very exciting. And to give you a feeling of how, at the end, many of these open questions are being treated by quantum simulation with a lot of different experiments and platforms, note that just a year ago, the Google AI quantum system used one of their superconducting circuits systems to actually simulate as well the Heisenberg model with very similar sizes. And in their case, the kind of observables they were able to address due to the geometry of their chip, they were able to access some particular observables that were not straightforward for us in our first experiment. But at the same time, they were able to go to cycle numbers that were not as large as we had done in the previous experiment. So overall, this just shows that it's kind of exciting and that there's quite a lot of interplay between theory and different experiments. Correct? So now let me give a bit of an overview of what this field of quantum gas microscopy, which again started around 14 years ago, has become recently. And there's been a lot of quantum gas microscopes for bosons. As you will see, some atomic elements are more popular than others. This is rubidium, which is one of the most popular ones. And there's a lot of great research institutes and universities all over the world that have been able to work with it. We also have cesium, ytterbium, erbium, lithium. We can also look at fermionic quantum gas microscopes. And here the list of different elements is a bit smaller, but there's been elements like potassium and lithium. So now we see this list of very exciting elements of the periodic table and very interesting cities all over the world. We were wondering, and this is how our whole project started, if we could be added to this list and we could put Strontium into the list of quantum gas microscopes and Barcelona as a place where we're doing this kind of research. And that's where QUIONE enters, and which I will try to explain in the next part of my talk. All right. And of course, I don't know how it's organized, but if there are any questions at any time of the talk, feel free to ask. I assume the moderators will take care of that. All right. So the next part of the seminar, I finally delve into the question of what is QUIONE and try to give an answer to that. So as Javier was mentioning at the beginning of my talk, you might have seen about this in some of the recent press releases, newspapers. So it's been quite a crazy amount of articles that we've seen in a very short amount of time. And I will say, in general, many of them got right what we were doing. In some cases, we read stuff that we were not so happy to read because we felt it didn't really convey what we were doing. But I think this is how these things happen. So allow me to be quite simple and be clear about what QUIONE is. QUIONE is a Strontium quantum gas microscope, so a new kind of analog quantum simulator. And the name comes from this, also written differently in some languages, the Greek goddess of snow and winter, which kind of, it's a quite reasonable connection given that we're working with nanokelvin clouds, which are probably the coldest places in the whole universe. And again, this is how our lab looks like, as I showed you in the beginning. And to understand a bit what really composes QUIONE, it's not just one particular piece or one chip or something, but it's a whole pack. No, we have a laser system that's used to cool the atoms. We have a vacuum chamber that has been prepared very carefully to only have this pressure of strontium atoms. An experiment control, where we can tune the whole experiment, as well as the optical potentials used to finally take a picture of the atoms. I don't know if there was a question or.
Yeah.
1 second. Okay, Vinayak, you can please go ahead.
I think you can speak. If your microphone might be muted, but
yeah. Hi.
Hi.
Am I audible? Like, can you hear me properly?
Yes, yes.
So, before you were mentioning about like this optical lattices and trapping atoms in those optical lattices. Yeah, you mentioned in the previous slide that you were mentioning about some kind of optical lattices.
Yes. Do you want me to go back or?
No. I'm just asking I had a very much like in course like in physics of ultracold atoms during my master's. So where I learned about this magneto-optical trapping. So this MOT and all. So the optical potential you are mentioning, how it's different from like MOT trap that we are working here. So is this the same kind of?
That's a good question.
Like kind of... Yes.
Yeah. I think hopefully the answer will come in a couple of slides because I haven't really touched about the difference between the magneto-optical trap and the dipole trap, but I have some presentation in a couple of slides that maybe will make it more clear. And if it's not, we can go back. But they are indeed different things. In our system, we have a magneto-optical trap to cool the atoms, and then they are prepared on an optical potential. But as I say, it will become more clear.
Like experience. Yes, I had an experience in this MOT, so that's why I'm out of curiosity. I asked, like, my current research areas is based on this domain. So,
yeah.
Okay, I'll see you in the.
We'll learn about this in a second. So, again, I was giving the whole overview of what QUIONE is and how our lab, the different parts of our lab are. And now let me go into the next part. So, essentially, when we have the whole system, we're able to take these pictures with the atoms in the optical lattice. And a particular question that might come is, why is it strontium? Why rubidium? I never liked chemistry. This is all a bit complicated. In general, you have the whole periodic table at your disposal, but some atomic elements are easier than others in terms of preparing these cold gases. And this is, for example, a piece of art that's in many places in Barcelona, and I believe also in other cities nowadays, that was done by Eugenia Balcells, which essentially shows the spectrum of each one of the elements of the periodic table. And in particular, here we can see strontium. And essentially, that's the short answer. Strontium has some transitions, some optical transitions that make it quite desirable for the kind of experiments we want to do. And in a nutshell, I hope I don't get anyone scared by this, but it's kind of the most technical, or the second most technical AMO slide that I have. We start with the atoms in the ground state, and we have this transition which is at 461 nanometers, so it's blue. And this allows us to reach very cold temperatures of 1 millikelvin. So thousands of a degree above zero absolute, but that's not enough. Then we need a second transition that's narrower in line width, which in practice, this means we can get colder. And finally, though we're not using it right now, a very important transition of strontium is the clock transition, which is extremely narrow, and it's used in the most precise optical atomic clocks in the world. At the same time, strontium also comes in a range of different isotopes. And I was talking before about Bose and Fermi-Hubbard. Essentially, depending on the number of protons, electrons, and neutrons that an atom has, it might behave bosonic or fermionic. And it just turns out that strontium has both bosonic and fermionic atoms, which means we are able to play the physics of these different quantum statistics. So this is a short list of why Strontium is a good choice for a quantum simulator. And also there's a lot of applications that have shown that Strontium is good. So in the terms of digital quantum computing, there are several startups and universities trying to build a quantum computer based on Rydberg atoms and strontium atoms. Also, it can be used by what are called continuous Bose-Einstein condensates and could generate what's called an atom laser, which could be used for sensing and metrology, which is a very exciting field as well. And again, the elephant in the room is optical atomic clocks. This is really a very impressive field that has evolved a lot in the last few decades, and that where strontium is one of the most important elements and the main one with neutral atoms. So all the magic happens in this vacuum chamber. And I know it might look a bit like Photoshop, like we're trying to resemble the universe, but this is just naturally how our vacuum chamber looks due to some speckle interference of several lasers that are being shined into it. And this blue dot that you see in the center is the fluorescence of the coal atoms being prepared at the beginning. So it's like a small cloud with 1 million strontium atoms that are fluorescing in the blue. And right below, there's this objective that allows one to do microscopy. And in this same vacuum chamber is where everything happens. First, this laser cooling step, which, as the question from before, is where the magneto-optical trap, it's a bit more the technical term, was done. And that in this first paper we showed we can do with all the isotopes strontium. Afterwards, we do evaporation in an optical trap, which was able to get Bose-Einstein condensates of strontium-84, which is what's shown in this GIF that I'm showing here. And finally, we load them into the square optical lattice, where we can do the physics as well as detecting the atoms, which was the result that was published this few weeks ago about the microscope. But maybe to help understand, I wanted to show this video that the communications department at ICFO helped prepare, which shows kind of what is the physics that happens in the vacuum chamber, so the whole preparation. We start with the atoms being very hot, probably at hundreds of degrees Celsius, but by using this laser cooling, we're able to get the cloud at much smaller temperatures, so they're kind of already moving a bit less, and the size of the cloud is typically around 1 millimeter. Afterwards, we use this other transition, which has a red color, which allows us to go to temperatures of only 1 microkelvin, so 1/1,000,000th of a degree above zero, absolute zero. The cloud even gets smaller. Then we change to lasers that are finely tuned dipole traps, and we make those weaker and weaker such that the hottest particles, or the particles that have the most velocity, abandon the cloud. And that's what's called evaporative cooling, and allows us to get much colder, to nanokelvin, and that's when the quantum regime starts taking place. That's not necessarily how atoms look like, but that's how the resolution of this simulation looks like. And finally, they are loaded into this optical lattice, in which, depending on the interactions, the atoms might redistribute themselves in that potential in the way that we're showing. And in this case, we have different colors of atoms, which are in different states. And finally, we use the objective, and we use blue light to make fluorescence imaging, which allows us to detect the atoms one by one that it showed in this final picture in the case of strontium-84. So that's kind of a summary of the whole process, which takes typically a few seconds. That takes us from hundreds of degrees Celsius to extremely cold temperatures. And this video is actually available in YouTube and in the website of ICFO. So if you're interested, I think it should be easy to find it. So what is our motivation to build this machine with strontium? So there are several examples, but one is that we can work with bosons, and that would be very exciting to do experiments in the Bose-Hubbard in equilibrium or out of equilibrium. But also we should be able to do experiments where this densely packed array of atoms can interact with light in different ways, in what's called sub-wavelength array atom photon. It's kind of a frontier experiment of quantum optics. A different one is with fermions, which is the one I will try to stress more today. And in particular, strontium has a nuclear spin of 9.5, which means there's 10 different spin states one can work with. And in practice, this means that this Fermi-Hubbard model that I showed you before, where I said, well, like electrons, we have spin up and spin down. Now we can have 10 different spin states. So it's not only like, in this case, blue and orange particles, but we can have a lot of different colors as M&Ms or like acetos, no? And this is exciting because due to the particular properties of strontium, they are spin-independent interactions. So the atoms stay in those particular colors in which we have prepared them. And this is what's called the SUN Fermi-Hubbard model. And it has been theoretically studied in some cases of low temperature, but so far, there are very few experiments, and most of them have not been done with microscopes, but with bulk measurements. And some first evidence of exciting exotic quantum magnetism have already been seen, but we think QUIONE, this quantum gas microscope, might be able to go beyond that and very soon show some of these very interesting phases of matter that we want to learn more about. All right. So with this, I have broadly explained what QUIONE is and what are the main goals. And now let me jump to the more maybe scientific part of the talk, the one of the results. And most of the things that I will be explaining today were the ones that, well, let me first broadly explain what I'm showing here in the slide. So this is kind of a schematic of how our experiment looks like. Remember, the atoms are there in the center of the glass cell. The objective is right below. And we can use now, once the atoms are in the optical lattice, we can use these red lasers to cool them down to make sure they remain where they are, and the blue to scatter photons. And it allowed us to obtain pictures like this one. And this is what was published a few weeks ago, and it was when all these different press releases and articles came out about it. So if you're interested, at the end, the most of the information that you can find besides my talk should be in this paper, this article that we called Strontium Quantum Gas Microscope. So essentially there we show that we are able to get a point spread function which is below a micrometer and which is good to be able to reconstruct the position of the atoms. And this is, for example, how a raw picture in our experiment looks like. And by using some deconvolution techniques of, in general, image processing, we are able to reduce much more the noise and get a much more localized signal from which we can get histograms like this one, where in the x-axis I show the photon counts and in the y kind of the occurrences. And this peak we see here corresponds to lattice sites that had one atom, while the other peak corresponds to lattice sites that were empty and just had a bit of background noise. And by using this technique, we're able to reconstruct the position of the atoms into a 1 and 0 digital matrix. Then we can also see how good our imaging works by taking two different consecutive pictures and seeing what changed. So for example, in these two different pictures, these red blobs indicate that some atoms were lost during the imaging, while the yellow ones indicate that some atoms hoped to change their position during the imaging. And by using these things, we can reconstruct how good the fidelity of our imaging is, how many atoms might hop between two pictures, and how many of them got lost, which is a pretty common technique. And not only can we don't only need to take two pictures, but we can take 10 of them. So for example, here is a GIF or a video that I took of 30 seconds, where we took 10 different images. And you can see on some atoms disappear, some others might jump into nearest lattice sites. And it kind of shows, we essentially would want to have the atoms not move at all, but it kind of shows the dynamics that happens inherently in the system in a lattice, so like tunneling effect. And with this, we can characterize as a function of these 30 seconds how good our pinning fidelity is. Finally, we can realize the Bose-Hubbard model by using this evaporative cooling to have a very cold cloud of only a few nanokelvin. We can characterize the systems and benchmark exactly what are our parameters of the Hamiltonian. And this is how one of these superfluid clouds looks like. So it's like a very small cloud of atoms that doesn't look like anything special. But by allowing it to expand, we were able to see this interference pattern similar to the ones that were shown 20 years ago, which shows evidence that there is phase coherence in the system, and hence that we have prepared what's called a superfluid phase of matter. And by averaging a lot of them, the signal becomes a bit more clear, and you see like several peaks in the system. So now in the very final part of my talk, I'm going to shift to what we think we will be able to do with QUIONE, with our Strontium quantum gas microscope, by using fermionic strontium. And essentially, again, the interesting thing is that now atoms are not all identical or just two states, but we can have very different colors, very different spin states. And what we use are the hyperfine levels or the Zeeman levels of the ground state of Strontium-87. And as I said, that's 10 different states. And the good thing is, due to some properties of strontium and these very narrow transitions, it's possible just by putting a small magnetic field to split the excited state transitions of this atom in such a way that just with a laser and by changing the frequency of the laser, we're able to talk to one particular spin state or to another one. So in principle, by using these tricks, we are able to take pictures of only one spin state or the other one, and then find ways of moving them around to detect all those different 10 spin states. And you can think of this in the terms of this SUN Fermi-Hubbard, but if you're into quantum computing, you might also think of things like QDIPs, like having exciting states that go beyond just the digital, so not just qubits, but many different level states. So Strontium has also been proposed in other platforms to do that kind of physics, and this technique could be exploited for things like that. Finally, I just show a picture of how very recently we've been able to get our system to be able to image Strontium-87 as well, and where we're only detecting one of those 10 spin states. And as we are speaking, there's in the lab, there's one PhD student and a postdoc that are working on extending these to more states and to finally be able to, for example, prepare systems of 2 different spin states, like in the spin up, spin down, and be able to detect those independently, like by using lasers with different frequencies. But we can also go beyond that and prepare 4 or more spin states and detect them one by one by using the same techniques. And that's the thing we're most excited about and that we're trying to push, and that will be able to lead to some new quantum simulation experiments. All right, so with this, I'm slowly moving to the conclusion of my talk. Essentially, in summary, I have hopefully shown you that what QUIONE is, and that it's a novel Strontium quantum simulator. I have showed that in our lab, we've been able to detect bosonic Strontium-84 in the Bose-Hubbard regime for the first time. And that by using fermionic Strontium-87, we are able now to use a spin result detection to detect the position of each atom, but also its spin state. Now, in the outlook, among the first things that we think we're going to be doing in the very next weeks will be the first microscopic studies of this SUN Fermi-Hubbard model. We will we're working on building a laser that we can send through the objective that will be used to do single atom resolve addressing. So not only seeing each atom individually, but also be able to locally change its state. And finally, use of this optical clock transition that's so used for atomic clocks, and that could in the very near future be used also for quantum simulation, which is one of our main motivations. So with this, I come to the very last slide of my talk. I would like to thank you for your attention, but also thank the whole team of the group, in which you can feel we have like a lot of very young people going from bachelor, master students, PhD students, and mention for those the younger members in the audience that right now we still have some open PhD and postdoc positions. So if you're interested, get in touch with Leticia Taruel. So thank you.
Okay, so thank you very much, Antonio. It was very, very interesting and very, very clear. And I invite the people to ask questions, doubts, and see if there's some doubts that we can discuss. Remember, you just have to press your raise hand. Okay, so Binayak is again asking. So Javier, yeah.
1 second. Okay, Binayak, please go ahead.
We cannot hear you still, in case you're talking.
You're muted.
Yes.
No.
Hi again. So in one of your slide, you are saying you are using strontium, and I just it's caught my eye that the scattering length of strontium was a bit like very low kind of thing. So does that have any impact regarding other atoms? Like why you chose strontium? Yes, the scattering length of strontium. Yeah.
This is kind of a quite technical question that was kind of hiding under the rug. So I'm happy you asked it too. So I was talking about the different isotopes and their bosonic and fermionic character. There's also the abundance. So how easy is it to just, or what percentage of the atoms will be in that state if you just take a chunk of strontium? But an important column that I completely ignored is the scattering length. And this tells us how well the atoms will interact in these Hubbard models, but also how efficiently evaporative cooling can take place. And you might notice that Strontium-88 has a almost vanishing very small in these units of so-called A naught. So this one actually doesn't work well for evaporative cooling. It's not a good choice for any of the things that I described today. It's very useful for things like optical tweezers. But the ones that we're using, remember, are Strontium-87, which is here, and Strontium-84. And those ones have scattering lengths that are on the order of 100 A naught. And this is, as we've shown, very efficient to perform evaporative cooling and also to do interacting systems. So that's the reason why I've mostly talked about these two isotopes and not the other two. The price to pay is that the abundance is very small, particularly for the bosonic. It's only 0.5%. This in practice means that we need to find all the techniques, optimize the system as much as we can so that we don't lose any atom and get clouds of as many atoms as we can.
Yes, thanks. And this is also a new field because the nuclear spin you mentioned this I just listened it now, like this allows a very like open scopes for this G-man level transitions you mentioned. That's the best part during this talk. Like I get to know. Like you mentioned like this nuclear spin is 9.5, so we can have like different labels, we can have G-man splitting like that, polarized light, different polarizations you mentioned, like sigma plus and sigma minus transitions.
Yeah. So
that's right circularly polarized and the left circularly.
I'm not sure if I fully understood the question, but this was a bit what I was mentioning in this slide. So yes, there is these 10 different states, and the polarization of the light is indeed very important in terms of preparing or detecting each one of those states.
Any other question? So maybe I ask for clarification because I think I missed the point. So I guess the N in the SUN Hubbard simulation is the projection of the spin, or where is the capital N in? When
that would be the number of spin states you can work with. So typically the Hubbard model, the normal one, would be SU2 symmetric because you have two different spin states.
Yeah.
If you now work with 3, that would be SU3. And here with Strontium, we have the power of working with anything between SU2 and SU10. So if I just take all the spin states, it would be 10. Maybe I could have put n equals 10 to make that clear.
Yeah. Okay.
But that's the whole idea. And it's not that trivial because there are a lot of atoms like alkali that indeed have a lot of different hyperfine states. This is not something new. Yeah. But usually through their interactions, there's so-called spin-changing collisions. So you might prepare some atoms in one of those 10 spins, but after waiting a while, it has spread all over the place. While with Strontium, if you do things properly, they are able to interact for several seconds and remain in the initial spin states where you prepare them. So that's the power of these so-called SUN interactions.
I see. I also wanted to know if can you simulate longer range correlations in this, or this is as difficult as in any other?
It depends on what you mean. So the interactions are inherently short range and like local, but the physics that comes out of it, like in this example that I gave of the Hubbard model, they are long range. So that's an important thing to keep in mind. Like the Hamiltonian essentially can be described like a nearest neighbor or short range, but at the end, the antiferromagnet has a long range character. And you need a quantum gas microscope to detect that, because most other ways you would be able to detect some antiferromagnetic correlations between nearest neighbor will not show you that.
Yeah.
So, and if you're asking about long range interactions, which I don't know if that was your motivation.
Yeah, exactly. Yeah.
That Strontium is not your atom, at least not a priori, because with Rydberg atoms, in principle, you could come up with a situation where you could address this. But typically, you would want to choose another atom like erbium or dysprosium, which has been very successful in the last years for making long-range interactions. This is now one of the big things. There's also molecular physics, so there's cold molecules that could be used to make long-range interactions, and this is a very exciting field that's just starting.
Yeah. Very interesting. So I have many questions, but I think we should stop here and thank Antonio for spending this time with us, trying to clarify what was not very clear in the press releases. And it's very interesting also to know that you have positions for young people. So so stay tuned. So thank you very much, everybody. Stay tuned. We'll be back, I think, the 26th with another nice seminar by Henry Semenko from Quantinuum. So you will receive all the advertisement for that. And keep well, everybody. Thanks a lot, Antonio. Yeah. Goodbye.
It was a pleasure.
Goodbye, everybody.